record. So today what we're going to do is we're going to start on our review for the final exam. Does that sound great to everybody?
Professor, I just have a quick question. Will you be accepting demos today, or it's gonna be next class?
I can do demos after class if that's okay.
Yeah, that's fine. And another question, I know that we do have one more labs to do. How are you gonna be demo that one?
We can arrange to demo it after the 25th.
Okay, all right. Thank you.
Yeah. So the late work, so the work has to be turned in by the 25th, but if you do not have the chance to demo it, you can arrange to demo with me or the TAs. Make sense?
Yep, thank you.
So in case somehow we don't get to you, okay. So so I've went through and I had a couple years ago and I wrote a very brief, not so much study guide as a study list for this class. So if we go over to my GitHub page and over here into data structures, I have this study guide over here, which again, it's a bit of a misnomer. It is more of a list of things that need to be studied. So we have, so things that you'll want to study for the final exam: big O notation, recursion, especially as it relates to trees, sorting. Specifically what you'll want to know is you'll want to know insertions. So because we learned a lot of sorting algorithms, but what am I interested in knowing? I'm interested in knowing insertion sort. I'm interested in knowing especially if you know quick sort and partition. Okay. Merge sort is also another big one. Okay. Just knowing how that works and what the benefits of each of those are. With regards to quick sort and partition, you should know what I mean by that is make sure you understand how in-place quick sort works and how the partition function works. The Huffman encoding, again, I'm not doing that one for this exam. For data structures, with regards to each of the data structures we learned, you don't have to implement any of them. But what you should know is how to write code that uses them. So you want to know array, you want to review your array lists, how to use your linked lists, how add, remove, get, and set behave based on those. How and when to use stacks, how and when to use queues, the difference between a tree versus a binary tree versus a binary search tree. A heap, how to turn a heap into an array into a heap in O of n time, which has come up on the final before, with regards to and that's covered in the video. Hash tables and especially how they resolve collisions, as you'll see. And so there were some final exams from other institutions. Some of these links may be dead, but we'll be going over these. Oh yeah, and graphs. Know the difference between adjacency list and adjacency matrix, and know how to do breadth first search, depth first search, but especially know how to do Dijkstra's. So, okay. So let's go ahead and take a look at, let's see, is this one? Nope, that one is not live. Okay, and so let's see. This one was from Harvard and they removed it. Okay, so Harvard data structures practice final. Let's go ahead and find that because they always have one. And there's been a number of them that they've done. We don't need the answers. Yeah, so they've done that. That's supposed to be. All right. Let's see. Different order, but yeah, this should be good. Yep, those are some of the questions I recognize. Okay, great. So we're going to start by going over this practice exam because I've found this one in the past and the questions they ask are pretty good. So let's go ahead and get started. All right, suppose that items A, B, C, and D are pushed in that order onto an initially empty stack. Then S is popped 4 times, and as each item is popped off, it is inserted into an initially empty queue. If two items are then removed from the queue, what is the next item that will be removed from the queue? So let's go ahead and just draw these because that's what you should do when you've got data structures and you're wondering how these data structures work. And I'll just go ahead and draw my queue. And that is indicating what direction the queue is in. So we are pushing A, B, C, D, and E in that order onto an initially empty stack. So when you push them in, right, the stacks are last in, first out, LIFO data structures. So A is on the bottom. So then the stack S is popped 4 times, and as each item is popped, 1, 2, it's put into the initially empty queue. E, D, C, B, right? And queues are first in, first out. So that means that the E will be the first out. Everybody following so far?
Yes.
All right. So now we remove 2 items from the queue. And remember, with the queue, we always dequeue from the front. So what is the next item to be removed from the queue? Or what is the next item that would be removed? And that would be C. All right. If the binary tree below is printed in pre-order traversal, what would the result be? Okay, so pre-order means that we're going to do the root first, right? It's going to be root, then the left subtree, then the right subtree. Specifically, it was going to be pre-order on the root dot left and pre-order on the root dot right. Right? So that means that it's got to start with 6. So it can't be A or B. Right? And C doesn't make sense because it goes 6, then 9, then 17, and that just don't make sense. Right? So it's got to be D or. So let's go, but enough about that. Let's go ahead and actually traverse it. So we would do 6 first, and then we would then we would pre-order on our left subtree. To pre-order the left subtree starting at 17, what we would do in that case is we would do 17, and then we would do 17's left subtree, which is 9, then 17's right subtree, which is 4. Then we would do 6's right subtree because we've done 17's left subtree. So that'd be 22 followed by 16 followed by 14. Or sorry, not 14, 12. Yeah. Don't know where I got the 14 from, but it would be E. All right. So that should be fairly, fresh in your memory, but this is new. This is new and I love this question. All right. A graph implementation that uses a 2-dimensional array to represent edges would be most reasonable for which of the following cases? 1,000, a graph with 1,000 nodes, 1,200 edges, 100 nodes, 4,000 edges, 1,000 nodes, 10,000 edges, 10 nodes, 20 edges, and none of these, since a graph can only be represented as a linked structure. Now, that last one is the I don't know what's going on answer, because if you remember, over here, I have adjacency list and adjacency matrix. right? So there are two ways to represent graphs, right? And they both have their advantages and disadvantages, but especially with regards to memory is where the advantages lies. An adjacency list, which is the link structure, is this basically saying A has a, here is the list of nodes that A is connected to. It's connected to B and C. And B says it's connected to B is connected to C and Z. And C says it's connected just to, it's got a directed edge to A. Right? And Z might go, and we might get more of these. Okay. Whereas, but basically it's saying, here's a list of all the nodes that I have an edge connection with. In other words, it's kind of it's a map with a link. The key, it's a map. The key is the node, The value is the list of all the edges, sorry, all the other nodes that this node is connected to, or a list of all the edges. So what about an adjacency, a 2D array? Right, to review 2D array, it basically says, hey, we've got our nodes A, B, C, D. And it looks like a grid, A, B, C, D, right? And this is going to look terrible, but that's okay. Right? And basically, if you've got a connection from one node to another, we say, hey, we can get from A to B with a cost of 2 with a 2, B to A with a cost of 1, right? And so on and so forth. But basically, we put in the values for the edges, okay, that we want to represent these edges. Now, what has been found is that basically, when do we use one over the other? And the answer is, well, okay. So first off, the matrix representation, it's very efficient to look up what the edge cost is. You basically just do a row column kind of deal, right? You say, okay, C is this row, and I need to get the column there. It's a constant time lookup because you're looking at a table and you're essentially going to the index. Okay. Whereas a list, if you've got a list, you got to basically iterate through the list to find stuff. So that could take a bit longer. But in a sparse, but there's two types of graphs a simple graphs we deal with. We deal with sparse and dense graphs. And basically, if we have a bunch of nodes, right, but only one edge, okay, then that's a lot of wasted space. That's a sparse graph. In that case, it's probably way more memory efficient and better to have a list. And we find that basically we want to have a 2D array when it's 25%, when 25% of all possible edges exist. That's when it becomes really efficient to use our matrix. So we use matrices for dense graphs and lists for sparse graphs. And it's dense if it's 25% or more of the edges that exist. What do I mean by that? Well, if you have 10 nodes, there are 10 squared possible combinations, right? A can have an edge to A can have an edge to B can have an edge to C, and so on and so forth, right? And then B can have an edge to A, B can have an edge to B. So there's 10 squared, there's 10 squared. So if you have n nodes, then you can have, so if you have V vertices, then there's a maximum of V squared edges. So, and we want 25% of those edges to exist. So here we have 1,000 nodes and we have 1,200 edges out of a possible number of edges. So this is 1,000 nodes. What's 1,000 squared? That's 1,000,000. get rid of those zeros. So we have 12 out of 10,000. That does not look like 25%. This looks like actually a very sparse graph. And we notice that basically with a sparse graph, we basically have a almost 1-to-1 ratio for our nodes to edges. For B, we have 100 nodes, which means that there's a possibility of about 10,000 possible edges. We have 4,000 edges. 4 out of 10, which means that 40% of all the possible edges exist. Make sense there? That's a pretty good candidate. Now we have 1,000 node and 10,000 edges. So 10,000 edges out of 1,000 squared possible. 4. That's only 1% of all possible. And then finally, 10 nodes, 20 edges. Ten nodes squared becomes 100, 20 out of those. So we have 2 out of 10, which is 20% of all possible edges exist. So the most reasonable case would be B, because we have the most edges. Does this make sense? I know I spent a lot of time on this, but it's one of those things later in the semester you may not have picked up on. And I see there's a message in chat. Okay, great. Yes, it was a yes. Awesome. All right. All right, so here's another one. I like this one. I like a lot of these questions because they're good thinking questions. Okay. And that's really the point about reviewing for a final exam. You're like trying to go, oh yeah, that's how this works. Okay. So here's their node class. They don't use generics. We did. A lot of schools don't teach generics because I don't know, reasons. When is the final? I will send out an announcement today with the final exam and the time. Okay. And I also have to let the other professors know. So. Okay. So considering the following node. So here's the node class that they have. They just have val instead of left, right. Not that it really matters for us. So consider the following method. Mystery takes in a root, the root of a tree or subtree. That's the way it always works. If the right subtree is empty, return myself. Otherwise, return mystery on root.right. So you consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what the method does when passed a reference to the root node of a binary tree. Person 1 says it's the last node visited in order of traversal. Consultant 2 says it's the last node visited by post order. And number 3 says it's the last node visited by a level order traversal. Now, I mentioned level order traversal briefly, but that's just breadth first search. Okay. So which of these following opinions is correct, regardless of the contents of the tree? All right. So in an in-order traversal, the last node visited by an in-order traversal is the biggest node in the tree. And the biggest node in the tree is always the furthest to the right. It's always going to be the biggest node, and it's always going to be the one most to the right, because if there was something bigger, it would be its right child, and that would be the biggest node. But there's not. And anything smaller, like over here, is going to be left, and even anything to the right over here is going to be smaller than this, because if it was bigger, it'd be on the right. So the in-order traversal is always the rightmost. And if we look at this mystery algorithm, it basically says, hey, go as far to the right as possible. As soon as we get as far to the right as possible, right? Mystery, if I have a right node, go follow it. If I have a right node, go follow it. I don't have a right node, return me. this will return the rightmost node. So number one is correct. It is the rightmost node in order traversal. Now, post order traversal goes, I'm going to handle my left subtree, then my right subtree, and then I'm going to handle myself. Post order traversal always, the last node in the post order traversal is always the root, which is so yeah, this algorithm would return this node over here, and a post order traversal would be the root. So annoying buzzer noise. Okay. Rather, I should go Matt. All right, returns the last order visited by a level order traversal. Now, if I draw a perfect tree, then yeah, the last node in a level order traversal is this node. But we should probably think about a counterexample, like what if I remove a node? What if I remove that node? Well, then this would be visited. This would be returned by this. But in a level order traversal, which is breadth first search, this is the order things would be visited. 1, 2, 3, 4, 5, 6. This would be visited. This would be the last node visited in a level order traversal, but mystery returns this node. So 1, but not 2 and not 3. So the answer is A. All right, next. With a poorly chosen hash function, it's possible to have a situation where the search time in a hash table goes to. So let's go ahead and think about that poorly chosen hash function. And let's actually go ahead and write a bad hash function just to kind of illustrate the point. H of key is equal to index 0. That is my bad hash function. Everything hashes to index 0. Well, what happens in that case, right? Well, if I'm doing buckets, if I'm doing bucket hashing, I have this entire array, but I'm going to of linked lists, but I'm going to ignore it and just stuff everything into this first linked list, which means that if I'm trying to find something, then in the hash table, it's going to take O of n time. Inserting is fine. It's going to be constant time to insert it, but retrieval is going to be O of n. Likewise, with if I'm using open addressing, right? The first item is going to go here. Then the second item is going to go here. And then the third item is going to go here. And then the fourth item is going to go here. Well, actually, while they're doing this, each item I'm doing, it's checking to see if it can go here. But it can't, so it's going to try to go here. But it can't, so it's going to try to go here. But it can't, so it's going to try to go here. And then it's going to try to go here. And then the next item, ad infinitum. So to find any item, I have to iterate through every single item I've seen before. So this is linear time with a bad hash function. Everybody understand that? Why it's O of n if you have a bad hash function? Okay. This was the first question on our first exam. Don't see a need to go over it because it's not going to be there. You've already dealt with that. All right. Another hash table question. Ooh. So a police department wants to maintain a database of 18,000 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not a given license plate is in the database. Speed of response is very important. Efficient use of memory is also important, but not as important as the speed of response. So which of the following data structures is most appropriate for this task? So so here, what we care about is that we want speed. And if speed is tied, then the memory is going to act as the tiebreaker. Make sense? Okay. So we've got 5 different data structures to look at for this scenario. The first is a sorted linked list. So a sorted linked list is terrible if you want to find something, because at the linked list, if you want to find something, it will take O of n time, because you have to start at the beginning of the linked list, go to the next node, go to the next node, go to the next node, even if it's sorted, because you can only start at the beginning or the end of a linked list. And then you'd have to follow the nodes because you don't know where they are in memory. So you can't just cut to a random point and skip anything. So yeah, this takes O of n time. Not so great. What about a sorted array with 1800 entries? Now, first off, if we cared about memory, this would be the winner straight out, because there's nothing pretty as memory efficient for keeping stuff together as an array, because you don't have any overhead there. So with the array, though, with 1800 entries, with it being sorted, that means that what we can do is that if we're looking for a license plate number, we can calculate what the middle index is very easily, and then go search this portion if it's less, if the value is less, and this portion if the value is greater. In other words, do a binary search on it. We can do a binary search on anything that's sorted. Sorry, on a sorted array. Binary search means log n time. All right. A hash table using open addressing with 1800 entries. Well, we want to store up to 1800 license plate numbers. And worst case, and we need to account for Murphy's law, which is that what can go wrong will go wrong. So in other words, they're guaranteeing that there's not going to be any bureaucratic bloat, that they're only ever going to store up to 1800. So for the problems of this exam, we're only going to assume that being the max, the hard max of license plate numbers. So that said, if we use a hash table with exactly 1800 entries, then as hash tables get closer and closer to full, the runtime for these approaches O of n. Right? And the reason for this is because, right, and you can think of, so there's an equation, okay, with the load factor, and I believe it is, the equation is, if I'm doing this from memory, so the expected lookup time is equal to 1 plus 1 over 1 minus the load factor. I think that might be divided by 2. It doesn't really matter. But if the load factor is essentially, so load factor L is basically how full this thing is. So let's go ahead and start with an easier example, which is D. If the hash table has 3,600 possible entries, the maximum load factor is going to be 1/2. So in this case, L would be 1/2. So 1 minus 1/2 becomes 1 over 2. 1 divided by 1 over 2 becomes 2. Yeah, it's all over 2. And so now we've got 1 plus 2, which is 3, all over 2. So the expected lookup time when it gets maximum 50% full is 1.5 steps, 1.5 probes on average. Open address. So basically this is constant time for this one. But for E, let's take a look at E. That's 10,000 entries. So I'm going to go ahead and cheat on the math a bit. I'm going to, for this one, I'm going to turn this into 2,000 just to make my math easier, because it's close enough for the answer, especially in a multiple choice scenario. 1 over 1 minus L over 2. right? So what is L in this case? L is the maximum number of nodes. Okay. So L is 2,000 over 10,000, which is just the same as saying 2 out of 10, which is 1/5. So minus 1/5 become that turns the bottom part of this equation into, let's see, give me 1 second. That turns the bottom part of the, so that turns it into, so minus 1/5 becomes 4/5 over there. One over 4/5 becomes 5/4. Let's go ahead and add that. So that becomes 9/4. And let's go ahead and take that from the bottom and multiply it over here by 1/2 to make it a bit easier. So that becomes 9. And so this becomes 9/8, which is 1.125. Okay. And I'm just being, I'm taking time on this because I think it's important to illustrate, even if I'm not going to go into this much detail on the exam. Now, if you've got 1,800 entries out of 1,800, well, that'd be 1 minus 1, which would be a 0, and you can't have it divide by 0. But in this case, we would get 1 over 1 divided by, let's go ahead and say 1799 out of 1,800, which would give us 1 minus, so that would give us on the bottom 1 over 1,800. So that would give us 1 divided by 1. This becomes 1,800 plus 1. So this becomes 1,801 divided by 2, which is about 900 steps. That's not great. So anyway, in the end, basically it's between these two, which both on the end have constant time, but the tiebreaker is memory usage. So D is better to use because there really isn't too much of a significant difference between 1.5 steps on average versus 1.125 on average. Those are both constant time. This is a Huffman tree question. Let's move on to the next one. So an array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm, which is constructing a heap, which of the following is a possible ordering for the array? So these all have the same 7 numbers. And the idea here for heap sort is that we turn everything into a, so when you're doing heap sort, you're given an array. And what you want to do is you want to turn that array into a max heap. And then what you do is that you remove every item from the front of the max heap and put it on the end and pretend it no longer exists, so that and if you do that, basically you're removing the biggest item and putting it on the end each time. So eventually you'll end up with a sorted array. It takes, overall time is O of n plus n log n. It's actually quite efficient and it can be done in place. So this is asking after the initial phase, which is constructing the heap. So it's asking basically, which of these is a max heap? So a max heap, right? The parent always has to be bigger than both of its children, and that's a recursive property. So we can kind of just draw these out if we wanted to. 85, and then we have 78 and 45. It's bigger than both of those. And then 78 has 51 and 53 as its children. And 45 has 47 and 49 as children. That won't work because this is not a max. That subheap is not a max heap, right? It's a recursive process. So it's not A. 85 is going to be the biggest number, so D is also not going to be in there. So 85, 49, 78, 45, 47, 51, 53. It looks like it's going to be B. Okay. C is 78, and then 78 has these two as children, but 47 has these two things as children, which means that it is no, that C, it can't be C. And then E has those two things as children. 51 has 51 has 53 as a child, so that won't work. So it has to be B. All right, the following binary tree was constructed by a sequence of items in an initially empty tree. Now, notice that there's a lot of theory questions in here. Our actual exam itself will be about half theory, half coding, 50 points of theory, 50 points of coding. So, and that's actually the breakdown of these as well, if we look at point wise. So binary search tree below was shown below was constructed by inserting a sequence of items into an initially empty tree. Which of the following will not produce this binary search tree? So again, so the idea here is making sure there's no gaps that would be formed, right? 5 so let's look at A. 5, you add 3, then you add 4. Yep, that's going to result in that. Then you add 9, then 12. Then if you add 7, 7 is less than 9, so it'll go to the left of 9, which it does. 8 would go to the right of 7, 6, and then 20. Now, the thing here is that, what are they saying? Well, if I did 5 and then 20 and then 9 and then 12, I'd get a completely different tree. 5, 20, and then 9, and then 12. That's what they're kind of looking for. They're asking which of those sequences won't produce this and would produce something else. So 5, 9, 3, 7, 6, 8, 4, 12, 20. And it's very easy to do because what you just need to do is kind of figure out where the gaps occur. 5, 9, 7, 8, 6, 12, 20. If you don't understand what that means, don't worry. It will become very obvious when we hit it. 5, 9, 7, we're on D now. 3, 8, 12, 6, 4, 20. Okay, so it's going to be E. 5, 9, 3, 6, and then 7. Because if we do E, it will be 5, 9, 3, 6, 7, 8, 4, 12, and 20. And that's a very different tree, and not just because I'm terrible at drawing. The answer is E. All right. So suppose the keys in the middle row of the keyboard are inserted in succession. I've kind of done that. This is for a 2-3 tree. Let's go on to this. There will be a variation of this question on the exam. So suppose you're given an empty hash table of size 7, empty hash table of size 7 right there. And you have a sequence of keys to be inserted. We don't care about the values in the case because because the values are associated with the keys, so they'll go where the keys go. So the following sequence of keys is to be inserted. Insert these keys using each of the following operations. If an overflow occurs, say so and indicate the element that caused the overflow. So here, what we're doing is that we have linear probing, quadratic probing, and then they taught double hashing as well. So we'll just go over linear probing and quadratic probing. And then I'll briefly mention what the other one is. So the idea here is that the hash function for each of these to figure out what index that we're going to be putting each of these in is going to be the key mod 7. So in each of these cases, Let me go ahead and zoom in so that I can write a bit more. So in each of these cases, what we can do is that the place it goes into is determined by the remainder after being divided by 7. Now, when we're working on the exams, this is the part that gives that actually is responsible for most of the mistakes. If that happens, show your work, I'll be able to identify it as a math error very quickly. Very, very quickly. So no worries. Okay. So 15 mod 7 gives me remainder 1. This gives me remainder 3. 1. Now 21 divided by 7 it has remainder 0. 22 is it would be remainder 1. 23 would be remainder 2. And both these numbers are less than 7, so we would get this wants to go to index 3 and index 5. So 15 wants to go to index 1. 17 wants to go to index 3. 8 wants to go to index 1. But it can't. So it goes into 8. And I think that's a fine way to for me to show for this exam how that where the overflow occurred. Okay. Now we want to put 23 in. 23 wants to go into here, but it can't. So it tries to go into here, but it can't because that's taken. So 23 tries to ends up going into here. Okay. 3 wants to go into index 3. It can't, so it tries here. 3 tries to go to index 4, it can't, so it goes over here. And finally, 5 attempts to go into index 5, but it can't, so it goes over here. Lots of collisions there. Now remember, so that's linear probing, where basically if we have a collision, we look for the next available space. Okay. Sorry, I'm using a Wacom tablet this time, so it was 15. So 16. So we had 15, 17, 8, 23. Yes, 3 and 5 as our numbers. The time is 3:30 because it's a common exam. I will send out an announcement today. Okay. And if that conflicts with other exams, let me know. I'm super easy to arrange that. Okay. So, okay. 15 wants to go into index 1. 17 wants to go into index 3. 8 we want to put into index 1, but we can't. So we look 1 squared away, which is into 2. So 8 goes into there. 23 wants to go into index 2, but it can't. So it tries to go into there. It can't. So it's going to go 1 squared away from 2. It's going to go to 3, but it can't go there. So now it's going to try to go to 2 squared away. So 1, 2, 3, 4. So 23 will end up in index 6. 3 will go into index 3. Or it will try to, but it can't. It's taken. So it goes into index 4. And then 5 goes into index 5. No problem. On our exam with questions like this, you'll just basically be asked to drag the keys into the appropriate slot. You won't have to indicate where collisions are. It's just for purposes of auto grading there. Okay. Double hashing, the way that would work, by the way, is that if the first hash function doesn't work, try the second hash function. And now we get into graph algorithms. This graph is not great for their graph algorithms. So I'm going to, or for showing off the graph algorithms. So I'll move on and cover those in a bit. All right, iteration instead of recursion. So let's look at, let me boot up IntelliJ and look at some of the coding questions so we can get to some coding today. I will cover the graph algorithm questions, but I know from experience from covering this that this is the only part of the exam I just basically go, ugh, what a drag. It's because this is not. Their algorithms are just not fun in the slightest. I'm sorry, not the algorithms, the one they set up. There's too many numbers. Okay. So let's go ahead and new project. I know you can't see it. Don't worry yet. I still have to set it up. So that even before some of you probably finished typing it. Okay. So final exam review. This window. Yes, I know you can't see yet. It's fine. I know nobody has messaged me about that. I'm just putting, I am just, let's see. Okay. There we go. That's much better. Okay. And now let me go ahead and set up the font size editor. Okay, I guess I'm going to use sphere code, enable ligatures, and line and 20 for right now because new. Okay, final review.
Look.
Huh? And participants. Okay. Okay. Now I can share. New share and okay, and view appearance, enable presentation mode. And that doesn't really help. Appearance, exit full screen. Settings. Give me 1 second. Sorry. Presentation mode. Font size. Yeah. 36. There we go. Sorry. Enter presentation mode, view, appearance, exit full screen. There we go. All right. And now tell me if this looks fine.
It looks fine.
Okay. So now let me go back to sharing the other one. Okay. So we've got this part of the exam deals with binary trees with nodes that are constructed. It doesn't matter. I'm going to construct them however I want. So write a Java method that uses recursion to search for a key in a binary search tree whose root node is defined by the parameter root. If it finds the key, return the reference this corresponding data item. If it doesn't find it, return null. In the space below, rewrite this so that it uses iteration instead of recursion. Okay, so fine. I will use your node class. Okay, so share. Here's the node. Private static. I'm going to turn that into a private static though. Public static. And this wanted to return an object because it's returning the data. So here, what it's like acting like a hash table, except it's acting like a map where it's got a key and value being stored. So given a key, we're looking for the object, which is the value. Okay. And if we were doing it the way we've learned to do it, then it would look like this: K, comma, V, where basically we've got K key and V value. Yep, let's go ahead and do it like that, just to make it seem like ours. Public static K V V, return a V, search node, which takes of type K and V, and give me 1 second. Just going to share the entire screen. Fine. There we go. It was doing weird popping things. So KV root K target, the thing we're looking for. Okay. So it wants us to use iteration instead of recursion. So to do iteration, what we're going to do is we're going to use the stack. Stack of. So what is our stack going to be keeping track of? Actually, we don't even need to stack because we don't need to backtrack. We just need a while loop. While root is not equal to null, we're going to do stuff. And if we happen to get out of this, then we return null because we can find anything. So what we're going to do over here is we let's see. So here with the K and V, we need extends comparable K for the keys to be comparable. That's why they used integers, by the way. So the keys can be compared to each other because if we're using a tree, they have to be able to be put in order. So that's why they were using integers as their key. So while root is not equal to null, what we're going to do is that we are going to basically do int comparison is equal to key target dot compare to root. Okay. Yeah, actually what we're going to do is we're going to say node KV is, we're going to call it, we're going to instead create a current instead. So we don't accidentally mess with the root. While current is not equal, while current isn't null, compared to current dot key. compare everything to compare the target's value to the key. If it's less, we have to go left. So if comparison is less than 0, current is equal to current dot left else if comparison is equal to 0 means that they're the same thing, which means we found the target we are looking for. So current, so we're going to return the current dot value because we found the key that we were looking for. So we wanted to return the associated value. Else, final possible thing, comparison is greater. So in which case we do current is equal to current dot right. And unchecked assignment node to node. It's saying what's going on here. Oh, right. K comma V. K comma V. Okay, that should take care of those. All right, next question also uses these nodes, which I will fix up. Doesn't really matter. Let's go ahead and make a constructor for it. Public node K key V this dot key is equal to K. This dot V value is equal to V. We're going to need that for the next one. Okay. Which I think will be the final question we'll go over for today. So write a Java method named near that takes and we've done this kind of question on our final exam or something similar to it, by the way. So write a Java question, a Java method named mirror. It takes a reference to a root node in a binary tree and creates a new node with its own roots. That's the mirror image of the original tree. For example, if root is a reference to the tree on the left below, then the return value of mirror root would be a reference to the root on the tree to the right below. Okay, so hint, the method is much easier to write if you use recursion. So the other hint here is that it creates a new tree with its own nodes. So it doesn't move things around. If it had to swap things, this would be a nightmare. If you had to, on the other hand, because we're creating new nodes, it's not too bad. But see, on the left, we've got 1, 2, 3, 4, 5, 6, 7. And on the right, we've got 1, 3, 2, 5, 4, 7, 6. Now note that basically 3 still, even though it's been flipped, 3 has no children. 2 still keeps his children. His children have just been flipped, and his position in the tree has also been flipped. All right. So let's do this. So public static. I'm just going to do K. I'm just going to do the same thing here, even though it makes it more wordy. K extends comparable. K comma V node K V mirror takes in a node key value that is the root. And it's just, I'm just being lazy. I'm being lazy by being verbose because I don't want to rewrite it. I don't want to write another node and make it confusing because I wanted to keep it with the way they were doing their exam. So, which is completely different than the way we've done it, which doesn't matter. What matters is the problem solving process. Right? I mean, you could leave these out. It's fine. And everything would be fine. I just don't like getting all those errors or those warnings, which is literally the only reason I'm doing that. So, okay. Squash it, return null. So first off, base case, if root equals null, yeah, I could post this code to, I'll share this in an announcement. So if root is null, then that makes it pretty easy to figure out what the mirror is. Return null. If root doesn't exist, then also its mirror doesn't exist. Otherwise, if it does exist, then we need to first off, well, the mirror image of myself is no problem. The mirror, like if I've got 5 and I've got my left subtree and I've got my right subtree, what I need is a new node. I'll call it 5. I'll call it 5. 5 prime, sure, why not? That's what they like to do in math. And then what I need is on the left, I need my right subtree, one new copy of that, and on the left, a copy of my left subtree. But both of those also are mirrored. So that's a long way of saying basically the first thing I need to do is basically node kv mirror, or sorry, let's go with new root is equal to new node root dot key root dot value. So basically creating a new thing that's just a clone of the other thing. Hopefully that makes sense. Next, what we want to do is that we need to basically do this mirror operation on the left and right. And that's hard, so I'll leave it. So if it's hard, that means it's recursion and it's that thing's problem. But all I know is that I'm going to perform mirror on the left side, which means that it will become my right side. So new root dot left is going to be equal to the end of the mirror operation on root dot right. And new root dot right should be the mirror operation on the left. And now that I've got a root and I've got my nodes attached and they've been magically mirrored, all I have to do is tell my parent, hey, I'm done. And now I just have to think about and make sure does that magic work? Okay, well, I'm flipping my children. And then when I call mirror on root.right, if it exists, he's going to flip his children. And my right child, which was my left is going to flip his children, and so on and so forth recursively. And if we get a null, it's going to be a null, and we can just flip the null. Yeah, so this works. Questions about this one? it's one of those cases where recursion makes everything much easier. What is the runtime of it? It is O of n, because every single node in this gets flipped. Every single node gets its own clone and gets attached to it. That's O of n. All right, so let's talk about what we're going to be doing in the future ones. We're going to be looking at a couple of data, which is the best data structure. We're going to be looking at a couple of other node questions, doing Dijkstra's, answering some sorting questions about sorting theory. I like these questions about sorting a whole lot. Looking at more theoretical questions for hash tables. And then there's some from previous exams that I can't find, but it is good practice. So I will leave you with this question to practice on your own before the end, before the class ends. Or I'll give it to you before class ends, since we're at the end of class almost, and I will let you know. So basically, let's assume you are given a text file, okay? And it looks like this. It is a Rosen. Actually, let's go with Andrew, just my first name. And then it's got some numbers. And then we've got Alice, Andrew, Alice, Bob, Carl, Andrew, Bob, Carl. So what is this file? It is session times for login. So suppose we are basically given a log file of all the duration for each user, okay? And how long that duration is. So in other words, Andrew, me, logged in for 23 minutes, for 2348 seconds. Alice logged in for just about shy under 2 minutes. Then I logged in for about 2000 seconds. And then Alice was in for about 46,000 seconds, which is a lot. Very long session. So basically, these are basically how long people logged into my server. Okay. So, and it goes on with a lot of different usernames, an arbitrary number. We don't know what who all the users are. Okay. Or how often they logged in. So for each user, I want you to compute the average time each user was in. So give me the average time for Alice, the average time for for Andrew, the average time for Bob, Carl, and so on and so forth. So the average time for everybody. So this is a problem for a map where our eventual value, our eventual outcome is a map of all, where the keys are the people. And the value is the average time. Sorry, the key is the person, and the value is the average time they've logged in for. So we will go over that one next session. Okay. So, any other questions with regards to the final exam?
Will the final be kind of close to like how exam 2 was?
Yes.
Okay.
It will be close to how exam 2 was. My plan is basically that you're probably going to be in a large lecture hall with, so this is the way it's going to work. yes, I'll take demos in shortly. Let me just finish answering these questions. Okay. So the way it's going to work, and I'm going to email the rest of the professors so they know, is that it's a common final exam. Now, I really like getting my exams electronically. It really helps. Really helps with regards to grading and being able to transport exams. Okay. But I know some of you may have your laptops, or your laptop may not be fully charged, or Murphy's Law may take effect. So the exam will be electronic. It will be on Canvas with the same permissions and restrictions as the previous exam. Okay. However, there will also be a paper backup available for you. Make sense? So if you need to do your exam on paper, the paper is available. And don't worry about that. It's again, if you're on paper, it's actually going to be quicker because you don't have to deal with all those pesky warnings and errors that you're going to get when you're coding in an IDE.
So the exam won't be in our normal classroom then?
No, I will send out the location in the email later tonight as well.
Okay, cool.
But it's going to be, I believe, in Cirque, one of those. I can't remember the exact room name, so that's why I'm not going to mention it. But it's going to probably be in Cirque, in one of those very large lecture hall spaces. Nice, comfy chairs. All right. So I'm going to stop recording and I'll go ahead and dismiss the class. And then if you really need to demo something right now, you can. You can also demo tomorrow to your TAs or during office hours. But anyway, have a great day.